Hello, so today we are going to do the problem from Leetcode April Challenge, April 11. So the problem says we get a grid and of size m by n and an integer k, and we need to shift the grid k times. And here what they mean by shift operation is that grid ij moves to the next column, so it moves to grid ij plus 1. And grid I n minus 1 moves to grid I plus 1, 0. So the last column, the last position of the last column moves to the first cell of the first column, because basically the last column you can't move another column, and so you'd have to circle back. So it's sort of circular shift. And then the last cell in the matrix goes to the first cell in the matrix, right? Sorry, here what this means is that each cell from the last column moves one row down, right? So in the first column, of course. So yeah, this will be clear with an example. So here we have this example with this matrix. So 258 moves over. So 147 moves over to the next column. We have it here. 258, the second column moves to the last column. The last column is a little bit trickier, where we know that we have to move it to the first column because there is nothing to move it over to, but you can see here each cell moved one row down. So 3 move it to the second to the first second row, and then 6 move it to the last row. 9, which is the last position, n minus 1 move it to the first cell. Circular again, move of the row. So this is the main idea, the main problem. The first easy way to solve it is just to do the exact logic that we have here with the shift operation. This one is a pretty straightforward, so I'm just going to quickly walk through the code, and then we can do a more sophisticated solution. Okay, so let's see the straightforward solution that just simulates what the problem statement does. So I have here the three parts of the shift operations. I just numbered them here. So the first one is that the element at grid ij moves to this, for example, and we are just going to do the exact same operations. And so here we just keep rows and columns in a variable. And then the number of rows and number of columns. We want to do the shift operation k times, right? So we loop k times, and we initialize a new grid for each shift. So this would be each shifted grid. We initialize it here with just 0 values. And now we go through every. Now we execute the first step, which is every column except the last one. The element in ij moves to ij plus 1, right? So this means that we need to assign to ij plus 1 the value in ij. And so we just go through the rows, and for each column except the last one, we assign to the new grid on the ij plus 1 position. So that's here. We need to assign grid ij. That's exactly what this first operation does. And so we do that here. And this works with the j plus 1 because we don't need to handle the last column, and so we don't need to like loop around and go to the first column. The second part is the element at I on the last column, so I n minus 1 moves to grid I plus 1, 0. So it moves to the first column, and it moves one row down, right? And so we just do exactly that. So we go through every cell in the last column with this, and then one thing here, we leave out the last element in the column. So that's why we are doing rows minus 1 here, because we will assign it differently with 3 here. And so there we assign I plus 1, 0, which is what which is what we have here. I plus 1, 0. We want to assign I n minus 1, which in our case here, that's just I columns minus 1. Okay, n is the number of columns. So that way we handle 2. Now we handle 3, which is the element in my minus 1 and minus 1. So in the last cell moves to the first cell in the first column, and so we just take the new grid for 0, 0, and then we initialize it to the last cell. So that's a grid -1 n -1, which is just the number of rows -1, the number of columns -1. And then we assign grid to new grid, just so that the next shift operation, we shift the new grid, and then we return grid. So pretty straightforward. Just simulating the exact number of the exact problem statement. In terms of the number of the time complexity, so we have this loop for that goes k times. We have here rows and here columns, so this is rows by columns, and then this one is just rows, and so overall it's O of k. So overall this is just O of k rows columns, and if you want you could just name it nm as well. So yeah, one thing though is maybe we can get rid of this k term and at least have nm. We have to look at each position in the matrix, so I don't think we can do better than this, but at least this part we can try to reduce. So let's see how we can do that. Okay, so how can we solve this problem? So we can do this differently actually. So instead of doing in the previous solution where we did the shift ourselves each time, we can just calculate the final position in the new array for each cell. So for one we can compute, okay, what is the final position of one after k shift? What is the final position of this one after k shifts? So that's the main idea here. Now, the first observation we can make is that the index, the column for each cell, so if we do just 2 shifts, right, we know that 4 here will end up here, in this column will end up in this column, right, which is just 0 to 1, 2. So we shift once each time, we add 1 to the column each time. So the first observation is that we know that we can just take, for j, which is the column, we can just add k, right? Except for the case when the number k is bigger than the number of columns. So let's say, for example, we want to shift 0. Let's say k is equal, in this case, equal maybe to 3, right? So we'll shift once here, we'll shift once here, we'll shift once here, then we'll shift once here, then the second time we have to shift around back to 0, right? And so to do that, we can just take j plus k modulo the number of columns, modulo the size or the number of columns. Let's just call it this. And so this would be just modulo k, modulo columns, right? So that if, let's say for the case where j equal to 1 and k equal to 3, then here we would move from 1 plus 3, but for this case where the number of columns is 3, then we would move to 1, which makes sense. We would first, we want to shift 3 times, and so for the position 1, we will first move to 2, and then we will move back to 3, and then we'll move back again to the column 1, right? So that's the main idea here. And so we know the new value for j is going to be this. So j2 is going to be this value here. Now, what about the column? What about, sorry, the row index? For the row, it's simple for the other columns. So if I just take our matrix again here. For the other columns, let's say for other columns except the last one, rows remain the same, right? Because we move only j, except for the last row where it's a little bit tricky. So for the last row, what happens is that each, so this is 9. Let me write down the final result for k equal to 2. So if we shift by k, we will get this here where we have 9, 3, 6, 1, 4, 7, and 2, 5, 8. So what will happen for basically this here is that 3 went down. So 3 went down to the next row, 6 went down to the next row. That's what we have here. And the 9, because it's the last one, it has to go to position 0, right? So that's what happens. It's actually very similar to what happens with the columns. And so what this would mean is that for the last column, right, we know that the value for I2 is going to be equal to, because we are going to shift each time. So each time, for each shift, we add 1 to the row. So it's I plus k, right? Because k times we add 1. Now what about the modulo? We want to modulo the number of rows, right? Because for 9, we'll go back to 0 each time. So for the last one, we'll go back to 0. So we want to shift, we want to modulo by the number of rows, right? So this is for the last column. Now, how can we translate this to one formula that we can use for all columns, right? This is where the clever piece of this implementation is. So basically, we can, for each column, add in the formula something so that we can calculate when it reaches columns with the shifts we are doing. So we know that if we okay, so how can we extend this to every column, right? So the main thing is that we need this. We can divide by columns to know how many, and so we can do something like I plus j plus k divided by columns. I'll explain this in a moment, but so this would be like this. So why does this work? So what we want is, once the column reaches n shifts, right? Once the column reaches the last column, then this would be columns, right? Or if we say columns is n, then j plus k divided by n is what we are looking for. So once j plus k, once this reaches n, which means we reach the last column, then when we divide by n, we'll get 1. And once it's, so we'll get 1, right? And if it's 2n, we'll get 2. And so what this would mean is basically we'll add 1 to I when we reach the last column, which is exactly what we want. And we'll do it as many times as, we'll add as many times as there are shifts. So if k is equal to 2, then we know that we will shift the last column 2 times. So this is kind of the main idea here. And so to extend this to more than just one column, more than just the last column, it will be, we'll do I plus j plus k divided by columns. And we still want the whole thing to be modulo rows so that we don't shift. Once we reach the last row, we shift back up. So this is kind of the main thing. So we have now, so this would be our I2. And so with this, we have the formula for the new I value and the new j value. So now we can just use these two to basically we iterate through the rows and we iterate through the columns, and we have the new indices. And so in the new indices, we assign I and j, the values in I and j, pretty much. So that's the main idea. Now let's code it up and see if it passes test cases. Okay, so let's implement this. So yeah, first we need to initialize the 2 values that we are interested in. So the number of rows and the number of columns, and those are the length of the grid and the length of the number of columns, which is the length of the first row. We know that grid has at least size 1, so we are good with this. And then the next piece is we want to initialize our output array, which is going to be just columns here, and then we are going to do that for as many rows as we have. And now we can go for every column, yeah. Then we know the new index. We are just going to use the formula that we computed. It's j plus k modulo columns. So we shift by k. Basically, this is just shifting k times each column, and we are doing modulo for the last column as well. And now for each row, we are going to say the formula that we set for the new row position, which is going to be I plus this j plus k to accommodate when each column reaches the last column. And this is going to be divided by columns. So for the last column, each time we increase the row by 1. And then we want to do the whole thing modulo rows, so that if we reach the last row, we circle back to the first position. And so this would be modulo rows. And then once we do this, we have the 2 that we are interested in. So I2, J2 is equal to grid of I and j. So this is the new position. We calculated the indices for it once we shift by k, and we assign I and j. And then at the end, we just return the result. In terms of like time complexity, this is O of columns. This is O of rows here. And so overall, we are just having O of columns by rows. So overall is just O of m by n if we have m the number of rows and n the number of columns. Okay, so once we initialize correctly, it passes test cases. So let's submit. Okay, so that passes test cases, and it's a faster solution. Yeah, so that's pretty much it for this problem. Thanks for watching, and see you in the next one. Bye.